Okay, so exponential functions. So an exponential function, and again, this is review from grade 11, so I'll go over it fairly quickly, is a function where the exponent is the variable and the base is a number, but that number has to be a positive number, and also the number just can't be equal to 1. Because if it was equal to 1, 1 to any exponent's always 1, and it'd just be a straight line. Okay? So what I want to do is review what the graph of exponential functions look like, and then we're going to make some generalizations about them. So we're going to graph the exponential function 2 to the exponent x, and we'll graph the exponential function 1/2 to the exponent x. And in order to graph them, we'll just do it by table of values. Okay? So we'll start off by graphing the exponential function 2 to the exponent x, and we'll create a table of values from -3 all the way to +3. And remember that on any test or anything, I don't want you to use any decimals. Always fractional answers unless otherwise indicated. So we're doing our table of values. We'll do it in fractional notation. So 2 to the -3. The negative tells you to flip the base and then evaluate. So then you get 1/8. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. Anything to the power 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the power 3 is 8. So when I graph this guy, if you don't have graph paper, just roughly sketch it. I have my x-axis, my y-axis, and graphing. Okay, so there are the 7 points I'm going to use in order to graph the function. Remember that it's a curve, it's not a straight line, so you don't use a ruler to join up the points. You just use your free hand and try to sketch it as best you can. Putting arrows on the end of it, indicating that it goes in both directions continuously. Correct. So that's y is equal to 2 to the exponent x. Okay. Let's graph y is equal to 1/2 to the exponent x. And again, just as a note, remember it's very important to put your base in brackets, okay? Because it means something different if you don't. Again, graphing it between the values of -3 and 3. 1/2 to the -3 is 8. 1/2 to the -4 is 4. 1/2 to the -1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/4 and 1/8 respectively. So graphing y is equal to 1/2 to the exponent x. Yeah, that function. Okay. So exponential functions. Y is 2 to the exponent x. We're going to use this one to make some generalizations about bases that are greater than 1. Okay? So we're going to use this one to use when the b is a number greater than 1. And then we're going to use the green one to generalize graphs where the base is a fraction between 0 and 1. Okay? So the first thing I want to talk about is what the blue graph and the green graph What's different about them? So what's different about them is their end behaviors, right? Because you can see that the blue guy here is heading up towards positive infinity on this side, but on this side, it's heading, the green graph is heading up to positive infinity. So when you have an exponential function where the base is greater than 1, then the end behavior is always going to be the same. As x approaches positive infinity, what value does y approach? I'm looking at the blue graph and making some generalizations. So as x approaches positive infinity, where is my blue graph going? Is that better? Positive infinity. As x approaches negative infinity, what value is my blue graph approaching? 0. 0. Okay, so what happens on this side, it gets closer and closer to 0, but it never ever touches it. So it gets really, really close to the x-axis, but never touches it. What do I call the x-axis then? It has a fancy name for, it's the name for a line the graph gets close to and never touches, John? Right, it's an asymptote. And because it's a horizontal one, you call it a horizontal asymptote. Okay? And then what else can I say about the blue one that's different than the green one is that the blue one is always increasing, right? Because increasing means going up to the right, and the blue one's always going up to the right. So the blue graph is always increasing. And this is true for any single exponential function where the base is bigger than 1. So I know I just graphed where the base is 2, but it works for any single one where the base is bigger than 1. When the base is a fraction between, bless you, 0 and 1, make sure the fraction's between 0 and 1. Like 3/2 is in between. It's a fraction, but not between 0 and 1. Okay, so now I'm going to use the green graph to make some generalizations, and I'll talk about the end behavior there. So for the green graph, as x approaches positive infinity, what value does y approach? Right? 0. Okay, so again, as we get closer and closer here, it's getting closer and closer to 0. And as x approaches negative infinity, what's happening on the other side? Anybody? So what's happening as I go negative infinity here? Where do I have to go? Somebody other end would like to? Positive infinity. Awesome. So it's heading upwards. The blue graph is always increasing. So what's the green graph always doing? Kyle? Decreasing. Okay, so those are the things that are different about exponential functions. But they have some things in common. So let's talk about the things that they have in common. So the things that are the same about exponential functions. So this applies to any single exponential function where b is greater than 0 and b isn't equal to 1. So what's the something that's the same for the green and the blue graph? Yep. The asymptote. Okay. The x-axis. What's the equation of the x-axis? Yep. Oh, x equal to 0 is this guy. Y plus 0. And we talked about what a horizontal asymptote is. Just as a reminder, remember that the horizontal asymptote isn't part of the graph. It's just a line that the graph gets closer and closer to. It's like a boundary that you use to graph. Okay? What else do these guys have that are the same? John? Perfect. Okay, so it has the same y-intercept of 1, i.e. they both pass through the point 0 and 1. What else do they have the same? Perfect. So when you say they're both always positive, what are you talking about? The domain or the range? The range. So they have the same range. And they're both always positive. So to say that, the range would be y such that y is a number greater than 0, and y can be any other number. So that's just a mathematical way of saying that y is always positive. What else then? Now we're on that kind of topic. Range goes with, what's the domain of both of these guys? Awesome. So these three things are true for any single exponential function of this form. Now, if we start adding numbers at the end of it and putting numbers in front of it, that's going to change some of these things, right? But any single number to an exponent x will always have these things in common, and these things will be different, but they're the same for this guy was greater than 1 and this guy between 0. Any questions on exponential functions? Okay, so now we're getting into the new stuff, which are logarithmic functions. So a logarithmic function is the inverse of an exponential function. That's all a logarithmic function is. Today we're just going to kind of introduce the concept of it, and then practice to go from one form to the other form, and then evaluate. Okay? So is the inverse of an exponential function. So an exponential function looks like this, right? Y is equal to b to the exponent x, where b is a number greater than 0 and b can't be equal to 1. The logarithmic function so if I want to find the inverse, right, because that's all a logarithmic function is, if I want to find the inverse of the exponential, how do you start with finding the inverse of anything? What's your first step? Yep. Right, you switch the x and the y. So the blue one is the inverse of the red one. Okay. And then your next step is to, once you switch the x and the y, your next step was to, does anybody remember? We wrote the 6, 7 test on David. Isolate y. Okay, so now in this case, we're going to isolate y by introducing a new function. Okay. So the way I remember it is x equals b to the exponent y. The y moves down. The b, which is the base in the exponential, becomes the base in the logarithmic. Now you're like, what did he just do? We're going to practice to go from one form to the other form. So a logarithmic function has two forms. It has the exponential form, and it has the logarithmic form. To go from one form to the other form is going to be vital to be successful in this guide. Okay? So what we're going to do now is to practice going from one form to the other form. Before I do, let's just write down how I would read this. So this is read, the log, and the log is just the short form for logarithmic. So the log of x to the base b is equal to 1. So that's how you would read that. So most people, they want to read the little number first. They'll say the log of b to the x. Okay, so it's the log of x and then say what the base is. Okay, so we want to go from one form to the other form. First example, express in log form. And again, I'm going to use log to short form logarithmic or logarithm. Okay. So x equals b to the exponent y is the exponential form. The logarithmic form, and again, nothing mathematical about it, it's just how you remember how to write it, is the y moves down, takes this place, this comes over, becomes the base. Okay? So the way I would remember this is the t comes down, takes that place, and the r becomes the base on the log. So the r is the base on the log, and the r is the base in the exponential. So r is always the base. So when I did it here, right? See how the y came down took this place right here, right? Okay, don't get confused, and that's actually a good point. I'm not taking the inverse of this function. This is the inverse of a function, and I'm writing it in a different form. Do you know what I mean? Like this right here is the blue part. Do you understand what I'm saying? Yeah. Okay, so that's actually a really good point. I'm not trying to find the inverse of this function. This is an inverse of a function in exponential form. I'm trying to write it in the other form. That's what I'm trying to do. Okay? Okay, so somebody tell me what this would be in logarithmic form. Remember, this is already the inverse. It's the exponential form of the inverse. I want to find out what the log form of this would be. John. Perfect. Okay, so the exponent comes down. Base on the log is the same base in the exponential. John said it the other way around. It absolutely means the exact same thing. Okay. So now I'm going to do it with numbers to hopefully make a little bit more sense of what I'm talking about. If I say 2 to the exponent 3, 2 to the exponent 3 is equal to what value? Kyle? 8. Everybody knows, or should know if you're in this class, that 2 to the exponent 3 is equal to 8 because 2 times 2 times 2 is equal to 8. So now I want to write this in logarithmic form. Somebody tell me what that would be in log form.
Log 8 is the base 2 equals 3.
Perfect. Okay, so again, the 3 comes down, this comes over, becomes the base, and you get the log 8. So a log function, I don't know why I wrote x there. A log function, the log of 8 to the base 2, all it means is, what exponent do I have to put on this base to get this answer? That's all a log function means. Okay? So what exponent do I have to put on 2 to get 8? Well, that exponent would be 3. Does it make sense? Okay. So let's go into the other form. So express in exponential form. So we're going to take a log function. Now we know what it means. So I'm kind of getting my ahead of myself here, but log to the 25 to the base 5. Does anybody know the answer to that? Sure. Right, because all this is saying is what exponent do I have to put on this base 5 to get this as an answer? That's all a log function is saying. Okay, and that exponent would be 2. So take this and write this in exponential form. What would that be in exponential form? So in exponential form, you're doing it backwards. So the way, again, I remember it is the x stays, the b, which is the base, comes over, becomes the base here, and that guy becomes the exponent. So what would this be? Perfect. and check it, right? Because it has to make mathematical sense, right? 5 squared is 25. Like, it'd be surprising how many people will put this as an answer or that as an answer. Like, that doesn't make any sense, right? Because 2 to the power 5 isn't equal to 25, right? And 25 squared definitely isn't equal to 5. Okay. So the log of t to the base m is equal to b. I want to write this in exponential form. Somebody who has an answer, take a stab at it. Awesome. And I think it's one of those things that if you're still sitting there and you're too shy to say, I have no idea what he's talking about, right? I think it's one of those things that once you try them, once you get it, you're going to get it, you know? And if you still need help with it, we can go over it individually if you're still struggling with it. And again, it doesn't matter the order in which I write it. So if I write c is equal to the log of a to the base d, how would this one be an exponential? Awesome. So again, all a log function means is what exponent do I have to put on d to get a as an answer? And that exponent would be c. So what do I need to put on d to get a as an answer? That exponent. So you're just practicing going from one form to the other form. Okay. So I'm going to go over the next part, which is on estimating, very quickly because it's pretty much useless. And I'm just going to cover it because I cover it in the guide. So I'd like to estimate the log of 10 to the base t. Okay. So basically this question is saying, what exponent do I have to put on 2 to get 10 as an answer? I have no idea what that is, so I'm going to say, I don't know what it is, I'm going to call it x. But then if I write this in exponential form, what would this be in exponential form? To help me guess the value here. Okay. So 2 to some exponent is equal to 10. And again, estimating is just guessing. And I know 2 to the power 3 is equal to 8. And I know 2 to the power 4 is equal to 16. So what value do you think x is? Is it going to be closer to 3 or closer to 4? Yeah?
Close to 3.
Yeah, closer to 3. So 3 point what do you think, Dean?
I'm going to go with 3.2.
Perfect. And that's it. That's all you want to do for estimate. Okay? Any questions on that? Okay. So if you want to skip it, skip it. The next thing is using your calculator. I guess they do the estimating stuff because it just gives you a better understanding of what a log function is. Okay? Again, all it simply means is what exponent do I put on this base to get this answer. And if you grab your calculator out, and you should do that now if you have your calculator, and if you don't have your calculator, you should say, why don't I have my calculator? You'll see 2 buttons on your calculator. Well, you'll see more than 2 buttons, but 2 buttons dealing with this. The first one is log, and every single log function has to have a base, and if it leaves out the base, by definition, it's always 10. So on your calculator, the log button means log to the base 10. Then there's another button going to be right beside it. That looks like the button N, but it really stands for ln. And this is a very important logarithm. It stands for the log to the base e. Log to the base e. I have no idea what e is. But if you hit, you'll see an e button on your calculator. If you hit e to the exponent 1, what value does that give you? Anybody get it? David? And then like 2.8 or something? Okay, so E is just a transcendental number. Does anybody know the other transcendental number you've learned so far in your career? Pi. Awesome. Okay. So there are two numbers that go on forever that have no repetition. There's no way of knowing the next digit. Okay. Anybody take calculus and vectors next semester? You'll learn where E comes from. For now, you don't need to know anything except that the log of E is equal to ln. Okay. So this ln is a quicker way of writing this down. And it's very important, if any of you guys have taken biology or chemistry, you may have seen this before, and it's called the natural logarithm. It's a very important logarithm, but for now we're not going to learn about it. All we need to know is that ln is a quicker way of writing log to the base e. That's all you need to know. Okay? But if I ask you to evaluate using your calculator, then we can only evaluate two bases, the one with the base 10 and the one with the base e. So if I ask you the log of 1,000, then you would hit 1,000, hit log, or some people would be able to tell me that without using their calculator. Either way, what's the answer to this question? Okay.
3.
Okay. Using your calculator, some people would put 1,000, press log. Some people would put log, then 1,000, whichever way your calculator works, you'd get 3. Not using your calculator and using your brain, what exponent do I have to put on 10 in order to get 1,000? 10 to the power 3 is equal to 1,000. Okay? But if I ask a question like this, log to the 99 is what exponent do I have to put on 10 to get 99? That's some random, not random, but that's some decimal number. So you would just round it off to a couple decimal places. Somebody tell me what that is? Perfect. And you knew it was going to be pretty close to 2 because the log of 100 would be equal to 2. And then finally, the ln of 10. So this means what exponent do I have to put on E in order to get 10 as an answer? Okay, so the ln 10 means the exact same thing as this. But because in higher mathematics we use the log to the base e quite often, we just made a short form for it. That's all. Okay? What's that approximate answer? Yeah.
2.606.
Okay. So going back to what we did today, exponentials. So make sure you know the graphs of how to sketch one quickly. Know what's different about them and what's same about them. And now logarithmic functions. This is the new stuff. The important thing is that a logarithmic function is the inverse of an exponential. There's two forms, and it's very, very important. You can go from one form to the other form quite easily. Okay, there's some practice on doing that. There's some practice in your guides. And then understanding what a log function means. The log to the 25 to the base 5 means what exponent do I put on this base to get this answer. That's all it means. And then understanding what the two buttons mean on your calculator. That's all you need to know for today. If you understand that, you're good. Okay? Now, having said that, I said this is one of the hardest units. It is.